Okay, chapter 2 was on Newton's first law of motion. Chapter 4 is on Newton's second law, which is force causes acceleration. We're going to talk about friction, the difference between mass and weight, how mass resists acceleration, and talk about free fall and non-free fall. So force causes acceleration. Here's a guy pushing on a crate and it could speed up. The acceleration depends on the net force, which is the sum of all the forces acting on an object, and acceleration is directly proportional to the net force. If you want to increase the acceleration of an object, you must increase the net force acting on it. You can put a little squiggly line for acceleration is proportional to net force. Friction. Friction depends on the kinds of materials and how much they are pressed together. The cause of friction is that every surface, no matter how smooth it looks, has little bumps on it, and these bumps cause stickiness. So an example here is the friction between a crate on a smooth wooden floor is less than on a rough floor because there's fewer bumps on the smooth floor. Mass is the quantity of matter in an object. It also measures the inertia or sluggishness that an object exhibits in response to any effort made to start it or stop it or change its state of motion in any way. And weight is the force upon an object due to gravity. So here we have two anvils. If they're the same size and shape, and if they're both made of iron, then they'll both have the same mass. But if this one's out in space, it has zero weight, whereas this one's here on the Earth, it has a lot of weight. So again, mass is the measure of inertia of an object. It's independent of gravity. Greater inertia means greater mass. So here's an astronaut. He's got an anvil. He's way out in space. The anvil is weightless, but if he tries to shake it back and forth or accelerate it, he'll find it's difficult to do that. And that's because it has mass. It has the tendency to resist acceleration. Weight is the same thing as the force on an object due to gravity. The unit for weight is the Newton. Another unit of weight is the pound. So mass and weight in everyday conversation are interchangeable. However, in physics, mass is the more fundamental unit. On the moon or on the Earth, the weight of an object on the moon is less than the weight of the object on Earth. So if this astronaut is holding up these objects, it'll be easier to hold it. However, the mass is the same on both locations. So if you're trying to shake it back and forth, it would be just as hard on the moon as it would be on Earth. Some conversions. 1 kilogram weighs 10 newtons, or 9.8 newtons to be precise, here on Earth. And 1 kilogram weighs 2.2 pounds at Earth's surface. 1 pound is the same thing as 4.45 newtons. Here we have a 10-pound weight, which has a mass of 4.54 kilograms. So the same force applied to twice the mass produces half the acceleration. If you apply the same force to 3 times the mass, it'll produce 1/3 of the acceleration. So mass is resisting acceleration. The acceleration of an object, the squiggly line means proportional to 1 over the mass. Okay, and this has nothing to do with friction. If you have this big earth mover, it's 3 stories high, it's filled with dirt, okay? It doesn't matter if it's on a frictionless surface, it's difficult to accelerate this thing. You'd need a lot of force and would only pick up speed very, very slowly. That's because mass resists acceleration. So, we come to Newton's second law. It relates acceleration to force. In word form, it is, the acceleration produced by net force on an object is directly proportional to the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. So here's a guy pushing an elephant on roller skates. As he applies a greater net force, the acceleration is greater. And as you change the mass of the elephant, okay, increase the mass of the elephant, the acceleration is less. In equation form, it's A equals net force over mass. Example, net force is doubled, the acceleration is doubled, the mass of an object is doubled, the acceleration is halved. Some more examples. If you have this brick, you have a force on it, which is accelerating it, it gets faster and faster. If you use two hands and press twice as much force on the same brick, it'll have twice as much acceleration. Back to the original force, if you push that force on two bricks, they'll accelerate half as much. But if you put two hands on two bricks, they'll go back to the same acceleration. Or the original force on three bricks, 1/3 as much acceleration. Free fall. So, we know from before that the greater the mass of the object, the greater its force of attraction towards the Earth. That's the force of gravity. But also, smaller its tendency to move. The mass is inversely proportional to the acceleration. So, it turns out that these two effects cancel. Okay? So all objects of different masses have the same acceleration when they're in free fall. So here's a single mass. The force is F, its mass is m, so its acceleration is g, F over m. Here's two masses. The force on it is twice as much gravity. Divided by twice as much mass, you still get the same acceleration. Okay, so free fall is when the acceleration is g, 10 meters per second squared down. And Newton's second law provides an explanation for the equal accelerations of freely falling objects of various masses. And this is all true when air resistance is negligible. The acceleration depends on the force, directly proportional to the force, and inversely proportional to the inertia. Those things cancel. So non-free fall is when an object experiences, when an object falls downward through the air, it experiences a downward force of gravity and an air drag force upwards. So in real life, things are not in free fall because of this air drag force R upwards. So when the acceleration of the fall is less than g, we call this non-free fall. It occurs when air resistance is non-negligible. So for example, these leaves, as they fall from the tree, certainly air resistance is not negligible for them. So the air resistance depends on two things: how fast the object's traveling through the air and how much frontal surface area it has. Terminal speed is when the object is moving so fast that the force of gravity equals the air resistance. In this case, there's no net force, so no acceleration, so the velocity does not change. Here we have two parachutists, okay, and they've both reached their terminal speed, where the weight equals the air resistance. Now this guy's weight is more than this guy's weight, so the air resistance has to be more, so the terminal speed for this parachutist is greater, because air resistance increases with speed, so he'll fall faster for the in order to be at terminal speed. So, non-free fall example. Imagine a skydiver jumps from a plane. At first, weight is the only force, okay, because you're not moving very fast. But as the diver speeds up, air resistance builds up, increases, the net force is reduced, and the acceleration becomes less and less, until, when the air resistance equals the diver's weight, the net force is 0, and there's no more acceleration. This is called terminal velocity, and the diver just continues down at a constant speed. So a coin and a feather fall, or they're both dropped from rest and fall through this column of air. The feather reaches its terminal velocity very quickly, and it falls at a constant speed, reaching the bottom after the coin does. The coin falls very quickly, and air resistance doesn't build up to its weight over short falling distances because it has a larger weight than the feather, which is why the coin hits the bottom so much sooner than the falling feather. However, if you pump out all the air from this jar so that it's a vacuum, then there's no air resistance on either object, and so they fall at the same rate, g. Okay, so now we're on to chapter 5, Newton's third law of motion. I want to talk about forces and interactions, Newton's third law, and then we'll end this chapter with a little discussion about vectors. So an interaction is between one thing and another. It requires a pair of forces acting on two objects. Example, the hand and the wall are pushing on each other. This is a force pair. You push on the wall pushes on you. And it turns out that all forces exist in force pairs like this. So Newton's third law of motion is whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Example is this hammer exerts a force on this spike. The spike exerts an equal and opposite force upward on the hammer. So you can call one force an action force, and you can call the other force a reaction force. These are actually co-pairs. It doesn't matter which one you name the action and which one you name the reaction. But neither force can exist without the other. And these forces are equal in strength, but opposite in direction. For an example here, you have a truck exerting a force on a car, and the car exerts an equal and opposite force on the truck. You may find that hard to believe because obviously the car is getting more damage, but damage is not the same as force. It just turns out that since this car is lighter and maybe more fragile, the force that's exerted on it will really damage it a lot. But this truck is more massive and I guess stronger, and so that same force acting on the truck doesn't damage it as much. And also note that these action-reaction pairs act on different objects. The truck acts on the car acts on the truck. So another way to express Newton's third law is to every action there's always an opposed equal reaction. Example, the tires of this car push backwards against the road. So that's your action force. The reaction is that the road pushes forwards on the car. And this is actually how come your car goes when you step on the gas. So a simple rule to identify action and reaction forces is first look at the interaction. One thing interacts with another. If you say that object A exerts a force on object B, that's your action. Your reaction is that object B exerts a force on object A. Example, if you have a rocket, object A exerts a force on gas, object B, then the reaction is that the gas, object B, exerts a force on the rocket, object A. So look at this cannonball. The cannonball exerts a force on the little cannon. Okay? Or sorry, the cannon exerts a force on the little cannonball, and that accelerates the cannonball. But the cannonball exerts an equal and opposite force on the cannon. Okay? But if you look at Newton's second law, you will see that the acceleration of the cannonball that has a small mass will be large, but the acceleration of the cannon, which has a larger mass, will be small. So the same force exerted on a small mass produces a larger acceleration. If it's exerted on a larger mass, it produces a smaller acceleration, which is why there's a little recoil on the cannon, but the cannonball goes very quickly forwards. Bam! So it's important to define your system. Consider a single enclosed orange, and there's an external force causing the orange to accelerate in accordance with Newton's second law. There's no action-reaction pairs shown in this system. However, what's really going on is this apple is pulling the orange. So there is an action-reaction pair. The apple pulls the orange pulls the apple. But they don't cancel because they're acting on different things. If you consider your system to be the orange, there's an external force pulling it along, and that's why it accelerates. So what if you actually consider the system to be the orange and the apple? So now the apple is part of the system, and these are now internal forces. So if the apple pulls the orange, these two forces will cancel. All that could happen is maybe the apple might accelerate to the left, the orange might accelerate to the right, but the whole system will not accelerate. So there needs to be something else here. So consider the same system, but now there's an external force of friction on it. Okay? So there's the same internal action and reaction forces between the orange and the apple, but there's another pair of action-reaction forces between the apple's feet and the floor. Okay? So one of these acts by the system, the apple acts on the floor, and that's a backwards force, but the other acts on the system. The floor acts with a forward force on the apple. And it's this external frictional force that pushes this whole system and causes them both to move towards the right. So the second pair of action and reaction forces do not cancel. I want to finish up chapter 5 by talking about vectors. So there's two kinds of quantities, vectors and scalars. A vector quantity has magnitude and direction and can be represented by an arrow. Examples of vectors include velocity, force, and acceleration. A scalar quantity has a magnitude only. Examples of scalars are mass, volume, speed. So the sum of two or more vectors, if the vectors are in the same direction, you can just add them arithmetically. If the vectors are in opposite directions, you can subtract them. If two vectors are not in the same direction, or the opposite direction, you can use the parallelogram rule. And if they're at right angles to each other, you can find the magnitude using the Pythagorean theorem. So if v is the vertical vector and h is a horizontal vector, then the resultant comes from r squared equals v squared plus h squared. So vectors have components. Okay? Vertical and horizontal components of a vector are perpendicular to each other, and the components add to give the actual vector. Here's an example of a ball in projectile motion. Okay? What happens here is that the velocity, which is this magenta vector, is changing as the ball is moving. But it always can be decomposed into a horizontal component, this blue vector, and a vertical component, this blue vector. And what happens due to gravity is that the vertical component is reduced by 10 meters per second, but the horizontal component doesn't change. It continues. You can see it's always towards the right, and it's always the same length. But they add to give this magenta vector, which is first up and to the right, and lastly down and to the right. Here's another vector problem. Nellie Newton hangs from a rope, as shown, one rope that goes underneath this ring. So which side of the rope has the greater tension? Well, there's three forces acting on Nellie. Her weight acts downwards. There's the tension in the left-hand side of the rope and then the right-hand side of the rope. Because these tensions are at different angles, there may be different tension forces on each side. Nellie hangs in equilibrium, so her weight is supported by two rope tensions adding vectorially to be equal and opposite to her weight. So we know her weight is down. This dashed line must be the sum of these two tensions. It must act directly up and be equal to her weight. So if you use the parallelogram rule, you will see that this tension in the left-hand rope must be less than the tension in the right-hand rope so that they add to go straight up.